So before we talk about evaluating NFAs quickly, let's switch tracks and talk about a different problem, the power of NFAs. So what sort of languages can NFAs recognize? So we know that there exist languages that DFAs can't find. Well, surely with this power of non-determinism, this allows us to have more things, right? Because at the very least, NFAs can recognize all regular languages, because a DFA can just be treated like an NFA without any choices to make. So here I've got an NFA, and here's the state transition diagram for it. Clearly this thing is just a DFA in disguise, right? Because it's an NFA, but I've always got one and only one state to go to. So this thing is really a DFA, right? So all DFAs are NFAs, but not all NFAs are DFAs, right? Because an NFA gives you the ability to include non-determinism, the ability to include choices to make. So surely that allows NFAs to be more expressive, right? Surely that would capture a larger class of languages. Turns out, no, they don't. And the reason behind that is because there exists an algorithm that takes a NFA and converts it into a corresponding DFA that has the exact same behavior. That is, it recognizes the same language. That algorithm is called subset construction. Which I'm going to go through now. Now, NFAs are still useful because sometimes it can be a lot easier to construct an NFA for a language than it is for a DFA. For example, suppose I wanted to construct a NFA for the language of all binary strings such that the string ends in 0, 1, 0. Okay? For an NFA, that's quite easy. You can just have the starting state, consume as many symbols as you want, and then at some arbitrary point in time, you read a 0, and then you read a 1, and then you read a 0. Okay? If you were to create a DFA for this, it'd be quite a lot harder, because you have to have states that I've seen a 0, and then a state for I've seen a 0, then a 1, and if you see a 1 afterwards, you have to restart and go back to the beginning, and it would be quite a lot more complicated. So NFAs can be easier to draw the state diagram for, and a lot of the time you can get away with fewer states, but they can't actually express a larger class of languages. There's always a corresponding DFA for every NFA at the expense of having additional states. So here's how we can convert an NFA to a DFA using subset construction. How we do it is we're going to construct a DFA such that every state in the DFA, so every state in the DFA is going to represent a set of states in the NFA. That's like all the states it could possibly be in. Every state in the DFA represents a set of states in the NFA. So what we do is from the starting state, we see all possible states we could reach, and that's going to be this state in the DFA. So let's do subset construction. So what we do is we first list the initial state. So if I see a 0 and I'm in the initial state, where could I possibly go? I could go to S0 or I could go to S1. So that means I can go to either one, right? S0 or S1. If I'm in S0 and I see a 1, where could I possibly go? Only back to S0. Okay? Now what we do here is I explore every state I don't know the transition diagram for. I know it for S0, so this is really a set, but I don't know it for S0, S1. So let's try exploring that. What this really means is I'm in the state S0 or I'm in the state S1. So if I'm in the state S0 and I see a 0, where could I go? Well, S0 or S1. And if I'm in the state S1 and I see a 0, where can I go? Nowhere. So it's just S0, S1. Okay? If I'm in S0 or S1 and I see a 1, where can I go? Well, if I'm in the first state, S0, I can go back to myself and nowhere else. If I'm in the state S1 and I see a 1, I can only go to S2. I've already explored this state, I just did it, but I haven't explored this set of states, so I better explore it too. And we keep running this algorithm until every state on the right-hand side has already been explored. So let's try this. If I see a 0 and I'm in S0, I can go to either of these two, S0, S1. If I'm in S2 and I see a 0, I could go to S3. So now I can go to S0 or S1 or S3. If I'm in S0 or S2 and I see a 1, where can I go? Well, if I'm in S0, I could go through a 1 back to S0. If I'm in S2, I can't go nowhere. So I go to the set containing S0, which I've already explored. I haven't explored this one here, right? S0, S1, S3. If I see a 0, where could I go? I could go to 0 or 1, S0, S1. If I'm in S1 and I see a 0, where can I go? Nowhere. If I'm in S3 and I see a 0, where can I go? Nowhere. So it's just 0 and 1. Now we do the same again. If I'm in S0 and I see a 1, I can go to S0. If I'm in S1 and I see a 1, I can go to S2. If I'm in S3 and I see a 1, I can't go nowhere. So I can go to S0, S2, which I've already explored. Okay? So now I can use this table to construct the corresponding DFA, where each state is going to be a set of states from the NFA. So there's 1, 2, 3, 4 states. S0, S1, S0, S2, S0, S1, S3. Okay? And then you just put in the arrows as the transition table tells you to. 0, 1, 0, 1, 0, and 1. Okay? And the last thing to check is which one of these states will be final states. It's any state containing a final state. So the only state containing a final state, S3 is the only final state, is going to be S0, S1, S3. So this here is the only final state. Okay? You might have seen in tutorials or in the course, we sort of get lazy with the notation and just write S0, S01, S02, and S013 instead of writing out the states explicitly, and then we just draw the same transitions as before. This is perfectly adequate because you have constructed a corresponding DFA for that NFA. You've just got to be careful in your mind that when you say S013, you really mean the state that corresponds to the set containing 0 and 1 and 3. So just be mindful what these things really represent. This is just a shorthand for this. Okay? That's a final state. There we are. So that's how you can convert an NFA to a DFA. And because every NFA can be converted to a DFA that's got the same behavior, that is, it recognizes the same language, that means NFAs and DFAs are like equally powerful. They're like equivalent in some sort of sense. I'm going to say they're like approximately equal, because they aren't equal, but they're equivalent in the sense you can always turn one into the other. Okay?